Okay, let me do another inclined plane problem. Let's say that I have I don't know, amusement park ride, roller coaster ride, something like that, a car, which is going up a frictionless plane. It's always frictionless unless we otherwise say. We'll start adding friction soon. And let's say it's got an initial velocity at 3 meters per second at the bottom. And I want to know how far up the plane does it go before it stops and starts to come back down. How far along the plane does it go? So this is both a Newton's second law and a kinematics problem, right? Because we can do Newton's second law, F net equals ma, and in order to find the acceleration of the car given the forces on the car. I guess I should give you a mass. I need to give you a mass. Turns out I don't need to give you a mass, but I could give you a mass to trick you. Let's say that mass is 1,000 kilograms. It's a car. Okay. So you might say, but there's mass. I need mass. Well, you'll see that you don't need mass. Actually, right here, you can see you don't need mass. The acceleration down the plane is independent of mass. Oh, we didn't make a point of that. I'm sorry. This is the last inclined plane problem we did. The acceleration was independent of mass. Forgot to point that out. Okay. So let's say that this car has an initial velocity up the plane of 3 meters per second, and it's just going all on its own accord due to its inertia, and its gravity is pulling it back down the plane. So gravity is what's slowing it down. So we would have to, and if we want to know how far it goes, we want to know the relationship between initial velocity and distance. That's kinematics. We're going to need to know acceleration. And so we need Newton's second law. Newton's second law, we can apply Newton's second law, and we can go through the whole, at any point along the plane, it's got a normal force, Fn, it's got a gravitational force, Fg, and you will find exactly identical to the last inclined plane problem we did. Apply Newton's second law, you're going to find that the acceleration is g times the sine of the plane angle, of the incline angle, sine of 20 degrees, that was degrees, down the plane, along the plane. I guess I should say along the plane. That is the acceleration. And how do I know that? Because I'm going to apply Newton's second law just like we did in the last inclined plane problem where we asked what is the box acceleration. We found that the acceleration is always, if there are no other forces, if the only force that's keeping it going down the plane is gravity, then it's going to be g sine 20 is the acceleration due to gravity. You can apply Newton's second law to find that. If we have to add friction, then the friction is going to change that. But without friction, it's just g sine of the plane angle. We know the magnitude of acceleration, and so now it's a kinematics problem. I'm going to draw in red the kinematics. We know the initial velocity is in that direction. We know the acceleration is in that direction. Acceleration is g sine 20. And we want to know how far it goes in that direction, delta x. And so to do the kinematics, we're going to write down delta x equals 1/2. This is a one-dimensional kinematics problem, right? It's not two-dimensional because it's only moving in one dimension. Careful there, right? The x direction is the direction of acceleration here. In the y direction, it's not accelerating at all. So in the y direction, we don't have to write down any kinematics because it's not moving in the y direction. The x direction is, we didn't choose an x direction. Let's go ahead and choose this direction as plus x and this direction as plus y. You might say, why did I choose down the plane as plus x when it's moving up the plane? We could have chosen up the plane. That would be fine. If we chose up the plane, then the acceleration would be negative g sine 20. We have to recognize that since the g sine 20 is down the plane. Okay, so setting this up. It's a one-dimensional motion problem. We're just moving in a straight line. It just happens to be that straight line is at an angle to the horizontal. But it's a one-dimensional motion problem where Vx is V0x plus AXT, and Vx squared is V0, come on, iPad, V0x squared plus 2AX delta x. It's a one-dimensional motion in that direction. We can write the three equations in the y direction. Delta y equals 1/2 a sub y t squared. oops, that was a sub x, plus v0yt, and dot, 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 but a sub y is equal to 0. So these equations don't really matter. So how far up the plane does it go before it stops? Well, we can, therefore, there's delta x right here and delta x right here. We can identify what we know and what we don't know. We know that we know a sub x is equal to plus g sine 20 degrees. We know, I'm going through the equation, do we know the time? We don't know the amount of time it takes. We know v0x is equal to minus 3 meters per second because it's pointing the opposite direction from plus x. We know Vx final. Do we know Vx final? Do we know Vx final of the car here when it stops? Trick question, right? When it stops. Vx final is 0. And Vox a sub x t. That's it, right? There are 4 variables. Okay, so that's what we know and what we don't know. And if you look at the 2 equations that have, and delta x, sorry, delta x. Delta x is what we want to know. That's what we want to know. 5 variables. Whew, that makes more sense. Okay. So then we look at these equations and say, okay, so if we use this equation, we can solve directly. Therefore, Vx final, 0. Vx initial, minus 3 meters per second, quantity squared, plus 2 times g sine 20. I could have plugged in g as 9.8 meters per second squared, times delta x. And don't forget, g is defined as 9.8 meters per second squared. G is never negative 9.8 meters per second squared. Never negative 9.8 meters per second squared. A may be minus g in the x direction or something like that. In this case, it's plus g in the x direction, right? So the acceleration may be negative, but g is always a positive quantity. G is always a positive quantity. Okay, that's just a reminder. So therefore, delta x is equal to, and don't mess up your minus signs here, right? This is minus 3 squared, which is plus 9, but then we have to subtract it from both sides. So it's minus 9 meters per second squared. Delta x is that. If you solve for delta x carefully, what you're going to find is delta x is minus 1.34 meters, which makes sense because the car is moving in the minus x direction because I chose plus x to be down the plane. If I had chosen plus x to be up the plane, it would have all worked out fine, and delta x would have been plus 1.34 meters. Okay.